In this video, I get to talk about arranging permutations where there are duplicate items to worry about, where we absolutely cannot count the same stuff twice. So if I was just to set up a nice introductory example, let's arrange something like Canada. Canada is built out of a couple similar letters. Those A's are going to cause a little bit of an issue. And so to kind of try to explain this, for example, let's talk about some outcomes here. This is definitely one way to arrange the letters. Very recognizable. So there's one. Now, if I was to move any two letters, which is what an arrangement is, you can move things around, it should change things. And so if I was just to switch those two, that looks different. That would be a different code. Totally would count. And this is going to be true if I switch any two letters, it should create something new that we haven't seen quite yet. And A, totally. But this logic breaks down the moment I decide to arrange or move duplicate letters with one another. And as you might be able to predict, even though I wrote the second A first and this first A in that spot, you saw me move them, this is not unique. That is not a new password. It is not a new permutation of these letters. And we have to find a way, even though all I did was arrange them, we have to have a strategy that can find those ones so that we're not ending up counting things that are not new, that are duplicates, and we can't count those things. So here is the logic and the strategy. I'm still going to employ the fundamental counting principle. Here is my sample space, C, N, D, A. And yes, I have to say that there are 6 items in my counting when I go to arrange this word. Now, I'm not really putting any restrictions on this arrangement because I do want to just kind of show the idea here. Now, how many things can be here? How many options are there right now? Now, we do have to honor this 6. I could not try to pick apart this information. I could not try to summarize that as one choice, and I would not want to say that there are currently 4 options, the C, N, D, A. Now, this could make sense, but it's not really going to get us to a calculation that works. And to hopefully kind of convince you why that's not maybe a good idea, I kind of maybe have to kind of talk about probability. Now, if you were guessing someone's password, what is the probability that you would get it correct? And that probability would have to be out of 6. Now, if it was an A, you would have a 3 in 6 chance of guessing it right. But it would still be out of 6 because there's 6 outcomes. If it was a consonant, perhaps you'd have a 1 in 6 chance because these would count, they heavily weight the things that are allowed to pick. They consider, they have a large ratio of the sample space. So we do have to honor that 6. And I will start off by saying there are 6 elements to pick from. Now I'm including all 3 A's as individual choices, but we'll take care of that later. Once one of them is selected, there's still 5, then still 4, then still 3 and 2 and 1. Nothing will change during the first stage of your calculation. This is otherwise known as 6 factorial. This is otherwise known as 720. But this 720 includes duplicates. Duplicates like this that we're not supposed to be counting. So this answer is actually quite high, but it does represent the theoretical total, which is important to get to first. Now, what is causing the duplicates? What are the things that we're going to have to cancel or remove from this calculation? Well, it's those A's. Those A's. And so if you look at the A's more specifically, now it was totally cool moving a letter with an A or any other letter, but it was not cool moving an A with another A. And those are the arrangements that we have to be on guard for. A's smoothed with A's in all these different ways. Now, on its own, that means 3 times 2 times 1, or 3 factorial. That's how many ways the A's could have been moved with one another, creating untold duplicates. These are the ones that we're asking you to cancel. And in in counting methods, because we're dealing with multiplying outcomes by outcomes, we cancel these outcomes by dividing by those duplicate arrangements. And those are the ones that we're not supposed to be arranging. Okay? And this brings the answer down considerably, and it gets us 120. And so to recap, in notation, this question could have been solved using 6 factorial divided by 3 factorial. Because the top of the story says, we're arranging 6 things. We're arranging 6 letters. And absolutely we were. There's 6 letters in Canada. You can't spell Canada with 4 letters. You need 6. We were arranging 6 things. And then the bottom cancels part of that and says, well, we were not arranging the 3 A's with one another. And that takes it out and cancels our duplicates. Now, this does open up a huge amount of question types now, because we're not limited to unique things. We can arrange. We can look at a sports team, and we can say, for the first part of their season, they won a bunch of games, they lost a bunch of games, but how many ways could this record, how many ways could they have been 5-4? Did they have to win all 5 first? Could they have won and lost? Could they have alternated? There's how many ways are there to arrange 9 of these games where 5 of them are wins, 4 of them are losses? And this opens up like a really nice idea like this, where I could say, well, if I just treat this like a word, not really a real word, but that there are 9 different things, not different, but 9 elements. And again, because if I asked you what's the chance of someone winning, what was the chance that this team won? You would have to say 5 out of 9, because there are 9 things that I'm looking at. Now, in the counting method, that means 1, 2, 3, 4, 5, 6, 7, 8, 9. And this might seem counterintuitive, but I would have to start my countdown from 9. How many things can be first? How many options are there? We would not want to say 2, win or lose. That's going to get really sneaky as we try to say do countdowns, permutations, arrangements. That gets really, gives me a headache right away. But as I say, this is the story, which is to say that it's like we're arranging 9 things, which is true. We are arranging 9 things. Oh, there's a whole bunch of duplicates. Yes. But what's causing the duplicates? What do we have to take out? Well, the 5 W's and the 4 L's. And the 5 W's are not going to be counted 5 factorial ways, 5, 4, 3, 2, 1. A lot of ways to move those W's with W's. And we're not supposed to be counting the 4 losses arranged with one another, which can happen in 4 factorial, 4, 3, 2, 1. And we get this all sorts of divisions. Now, if you're going to try and type in a big complex fraction like this in one calculator step, please use brackets around the entire bottom, because you do have to kind of hint to the calculator that you're dividing by both of those numbers. The calculator will only follow what you type, and it will interpret them exactly literally. It doesn't know that there's 2 different numbers on the bottom if you're only going to use one division sign. But in this calculation, 9 factorial divided by 5 factorial divided by 4 factorial would get me down to a number like 126. And this is precisely the kind of strategy that we're going to need when we start, say, giving you pathway questions. Let me just get a little quick diagram for myself. Nice and small. Traveling from A to B. How many paths are there? This is a really, really good arrangement question, permutation question. And I'll try to explain to you why. Picking any path through this diagram. That's one. I'm probably not going to, sit there and try and count out another one or another one or another one. I'm not going to try and sit there and count every path. That's not a good, successful strategy going forward. But here's one path. And if I had to give someone directions, I would say go south, east, east, south, south, east, perhaps. Maybe I could say down, right, right, down, down, right. But if this was a bunch of city streets and I had to tell someone this is the path you need to take, that's probably maybe one way I could describe it. Now that's one outcome. That is, to say south, east, east, south, south, east. Now, can I come up with a second one by just arranging them? Will arranging do what I want it to do and create pathways? Let's see. Remember, you can arrange them all. You can arrange any 2 you like. Any arrangement should work, rearranging at least. And so let me move the S and the E, creating south-south, east-east, southeast. Will that get us there? Let's see. South-south, east-east, southeast. Beautiful. It works. It's another path, which means if arranging is doing stuff and is correct, then we're in business. Permutation, factorial, fundamental counting principle. We can use those strategies to do this. And that happens to be a sample space. South, east, east, south, southeast. 6 things to get from A to B. Yes, there's duplicates, but I'm going to pretend there are 6 individual elements to work with. Meaning, if I'm arranging 6 things, it's known as 6 factorial. But because of the 3 S's, I cannot count those. Those will create duplicates. And because of the 3 E's, I can't count those. Those are also duplicates. This calculation, known as 6 factorial divided by 3 factorial divided by 3 factorial, will in fact bring it really down to a very realistic answer, which is that there are 20 paths through that diagram if you would try and count them all. Hope this has helped. Thank you.